Welcome to Supply Chain Management. In this lecture, we'll focus on the actual network design modeling. We talked about factors influencing network design in the previous lecture, but now we'll focus on the actual models, the mathematical models, and how to do it in Excel. So we stopped the last lecture focusing on the goal and the information needed per region. We're going to look at a company called Sun Oil, which is a manufacturer of petrochemicals with worldwide sales. Vice President of Supply Chain is considering several options to meet demand. And one possibility is to set up a facility in each region. And this advantage essentially this approach gives you an advantage that it lowers transportation costs and avoids help duties. However, here the plants are sized to meet local demand and may not be able to exploit economies of scale. Alternate approaches to consolidate plants in just a few regions improves economies of scale, but transportation and duties increase. Also, we talked about political risk. The more, if you are putting all your plants in one region and there is something which causes disruption of the supply chain, like COVID-19 or an earthquake or political unrest, so this actually, you're doubling down, and so you want to make sure that this place is pretty stable. So when designing a regional configuration, manager must consider these quantifiable trade-offs along with non-quantifiable factors, the competitive environment, political risk, etc. So here, in this particular case, we are dividing the world into 5 regions: North America, South America, Europe, Africa, and Asia. And here is the data given to you. Supply regions, here are the demand regions. This is in thousands of dollars, all costs. So this is $81,000, $92,000. To ship something from North America to South America, that's $92,000. Your fixed cost, if you have a low capacity plant here, that's 6,000 multiplied by 1,000, that's 6 million. This is 2.5 million. This is 9 million, okay? The fixed cost occurs no matter how much is produced or shipped from the facility. Variable cost is incurred in proportion to the quantity produced. And in this particular case, we are assuming that variable cost is going to grow linearly as quantity is produced or shipped. Now here, demand, your capacity are all in thousands of units. So this is 12,000, in millions of units. This is 12 million, 8 million, 14 million, 16 million, 7 million. Here it's 10 million and 20 million. All right. So let's move to Excel to see how we are going to set up and solve this problem. We have the model here, and our first step would be to copy this. And let's create a copy. We can delete all these questions right now. And we are going to copy this so we can set up a model. This is pretty much a transportation model with fixed costs, but we have a high capacity and a low capacity here. So the first thing you're going to do is you're going to delete the center. You have to rename these things. This is, we can say, build low, yes or no. And this will be build high capacity, yes or no. And here is amount shipped out, and here is total capacity. Here's the actual capacity. So let's go ahead and format this. This will be number, not currency. Your total amount shipped out will be the sum of the demand regions. You can copy this all the way with copy formula. Similarly, your demand or total amount shipped in is going to be here, and you can copy all of these here. So your variable cost is going to be the sum product of all your variable cost per unit multiplied by how much you're actually shipping, how many units you're shipping. Your fixed cost is going to be the sum product of your fixed costs multiplied by whether you're going to build it or not. These are going to be 1 or 0 values. And so your total cost will be the sum of these two values, and this is what you're going to minimize. This is the value you are going to minimize in this problem. So let's set up the analytic solver. We will minimize our total cost. Let's change B22 from maximum to minimum. Our variables here are this entire lot, right? You're going to select from B13 all the way to H17. These are all the variables computer is going to tell you what to put there. Of course, I forgot to put your total capacity is going to be this multiplied by 10 plus this multiplied by 20. So if this is a 1, you get 10. If this is a 1, this gets 20. And then now you can copy these all the way down here. Now in constraints, you know that amount shipped is going to be less than or equal to your total capacity. And then your demand here, what is being shipped to, should be equal to this. We also know that these are binary variables, and these here would be integer. Your engine, you should do assume non-negative is true, and you run your solution to get your answer right here. So you can see that it's about 23,581,000 is your total cost. And this would be your solution where you are not building anything in North America. You're building one low capacity factory in South America, one low and one high in Asia, and one in Africa, and you're meeting all the demand shipping from these places. Okay? So with this, we'll look at the second part to this question. So let's address the second question. They have to build one plant each in continent, cannot have more than one. So it's very similar. You go here, and essentially what you do is you look at total plants, right? And here we take the sum of these two plants, right? And when we copy them down, these values, if you look at this part B, they cannot have more than one. So cannot be constraint here. These values have to be less than or equal to 1, right? And if you run this now, if it cannot be more than 1, they have to build one plant in each continent. So in this particular case, this will be equal to 1, and you rerun this, and it forces you to build a plant in each continent, and you can see the increase in costs here. Now, part C is you don't have to build it if necessary, and therefore this constraint here will be less than or equal to 1. And so if you rerun this model, it will force you to select one plant each, but you can't have more than one. You don't have two in Asia. So you can see here the answers. The first answer comes to 23,581. If you're forced to build, you spend about 6 million more because of extra fixed cost here. You can see the fixed cost jumping up. And then if you're restricted to building one but don't have to build in each area, then it goes to 23,751, which is slightly more than 23,581. All right. So this is sun oil, and we talked about the initial part of where we are going to build a plant. So we finished this example of sun oil, and the next example is called a gravity location model. In this case, we have three sources, and we have about 5 markets, and we are given the cost of dollars per ton mile and the tons to be shipped and the coordinates. And we want to minimize the cost of transporting the raw materials from suppliers to finished goods to market served. Now, steel appliances is the example we're using. It's a manufacturer of high quality refrigerators and cooking ranges. And essentially, you have a assembly factory located near Denver, from which it has supplied the entire United States. Demand has grown rapidly, and the CEO wants to set up another factory to serve the Eastern market. So that's the problem. 3 parts plant located in Buffalo, Memphis, and St. Louis will supply parts to the new factory. Markets in Atlanta, Boston, Jacksonville, and Philadelphia and New York. These are the markets. Assume that markets and supply sources can be located as grid points. So that's the coordinates. If you can locate it in a grid in a map, and here are the X and Y coordinates. So we are going to use the Euclidean distance measure, which is if the location is XY selected for a facility, the distance is this X minus this value squared plus Y minus this value squared and this whole square root. But in some cases, people use Manhattan distance. Euclidean does the shortest path, whereas Manhattan distance does the longest path. And so you have the total cost, which is given by your distance multiplied by your quantity shipped, that's in tons, and then the cost of shipping per ton, right? And so let's go to Excel and see how we are working in this problem. So here's the data on the steel appliances, and we want to figure out where to locate this facility. And so here is the facility location, XY axis, and we have to calculate the cost. So let's take a look. The cost, of course, is calculated as the sum product of, you are looking at, you first have to calculate the distance. This is the Euclidean distance. So remember what we talked about is that the distance is this minus this whole squared plus this minus this whole squared at the square root. And so that's that formula here, square root of. And you remember that B15 and B16 have dollar signs. So when we copy this down, it actually stays the same, right? So once you have that, you want to minimize this cost, right? And this cost is then this is the number of tons, right? And this is the miles, distance traveled. So tons multiplied by miles will give you ton miles, and this is the dollar per ton mile. So when you multiply this times this times this, you will actually get your cost for that, for Buffalo, right? Markets, if it's sourcing from Buffalo. And similarly that. So therefore some products have 3 columns. We use the first column is the distance, second column is your tons, and third column is dollars per tons. And now once we have that, you want to minimize this. So you go to objective, make sure that you select this and minimize this. And the changing cells are, of course, these two here. And now we can run this model to get the minimum. So we need to locate this at 681.3 on the x-axis and 882 on the y-axis, and this is going to be a cost. This is called a gravity location model, where it looks at all these x and y axes and tries to locate it right at the center. So if you wanted to visualize this, you could easily select this and do a scatter plot. So here's the scatter plot of x and y axis. And so you're looking at 681, which is somewhere here, right? 681 and 882. 882, which is somewhere here. So let's go ahead and just put this number is 681.3 and 882, right? So if we look at this and we go ahead and select this also, now we can see this here. This is where your plant is going to be. And so let's go ahead and change the color here. Let's keep it. So you see that it's kind of trying to put it in the center of Buffalo is 700 over 1200. This is Buffalo, New York, right? Memphis is 250 over 600. So this is probably Memphis. 225, 825. This is probably St. Louis. So here are the supply, 1, 2, 3, and then here are the markets, right? And so you have this right at the center. And so this is called a gravity location model, and this is how you're going to do the gravity location model. So that takes care of the gravity location model. So now let's look at the last model, which is both demand allocation and plant location models. Now this is essentially after the potential sites have been identified. A manager must decide on the location and capacity allocation for each facility. Now, besides locating the facilities, a manager also decides how demand from each market is to be allocated. And this allocation must account for customer service constraints and response times, etc. Demand allocation decisions can be altered on regular basis as cost changes and market evolves. Now remember, setting up the facility, the site is very takes a lot of time, but demand allocation can be changed. When designing the network, both location and allocation decisions have to be made jointly, and therefore manager needs a bunch of information. We look at demand at each market, response time, fixed cost, variable cost, taxes, tariffs, etc. So the various costs along with tax and tariffs basically give us the fixed cost and the variable cost. So let's look at an example. And in this example, we have two companies. One company is called Telecom One, and the other one is called High Optic. So here is Telecom One, and Telecom One has factories in Baltimore, Memphis, and Wichita, and it supplies Atlanta, Boston, and Chicago. So that this area shaded dark is Telecom One. High Optic is in Cheyenne and Salt Lake, and it delivers to Denver, Omaha, and Portland. And you have fixed costs here. Here's the capacity, here's the demand in each location, here's the production and transportation costs. And let's assume that this company at the start, these two companies are separate. They are operating separately, right? And so we're trying to figure out what the minimum way of allocating to the demand. So does Baltimore supply Atlanta to supply Boston, etc.? Then assume that there is a merger, but all these 6 factories are open. And then which factories, finally we're looking at which factories should close. So let's look at each one of these problems in Excel. So that takes care of the gravity location model. So now let's look at the last model, which is both demand allocation and plant location models. Now this is essentially after the potential sites have been identified. A manager must decide on the location and capacity allocation for each facility. Now, besides locating the facilities, a manager also decides how demand from each market is to be allocated. And this allocation must account for customer service constraints and response times, etc. Demand allocation decisions can be altered on regular basis as cost changes and market evolves. Now remember, setting up the facility, the site is very takes a lot of time, but demand allocation can be changed. When designing the network, both location and allocation decisions have to be made jointly, and therefore manager needs a bunch of information. We look at demand at each market, response time, fixed cost, variable cost, taxes, tariffs, etc. So the various costs along with tax and tariffs basically give us the fixed cost and the variable cost. So let's look at an example. And in this example, we have two companies. One company is called Telecom One, and the other one is called High Optic. So here is Telecom One, and Telecom One has factories in Baltimore, Memphis, and Wichita, and it supplies Atlanta, Boston, and Chicago. So that this area shaded dark is Telecom One. High Optic is in Cheyenne and Salt Lake, and it delivers to Denver, Omaha, and Portland. And you have fixed costs here. Here's the capacity, here's the demand in each location, here's the production and transportation costs. And let's assume that this company at the start, these two companies are separate. They are operating separately, right? And so we're trying to figure out what the minimum way of allocating to the demand. So does Baltimore supply Atlanta to supply Boston, etc.? Then assume that there is a merger, but all these 6 factories are open. And then which factories, finally we're looking at which factories should close. So let's look at each one of these problems in Excel. So if you're going to look at this here is the whole data set. And remember, we have to first do only High Optic first, and then we want to do Telecom One first, and then do both. So what I would suggest is, because you have the data set up, instead of doing it as separate problems and just copying only, for example, this first, and I would suggest we copy this whole thing, right? And so let's take an example, and we'll see how we are going to do this. We just copy this whole thing into a new sheet, just like we did the last time. Create a copy. We can delete these, right? And we just copy this whole thing again. Remember, this is a transportation problem with fixed cost, right? You can go ahead and delete this. We know that in this particular case, if we're saying factories which are there, you know, the factories are available here. Let's just remove all the currency and make them numbers here. And these are 0, right? These are not available automatically, okay? So the capacity in Cheyenne, if you look at actual supply, sent out, and then we can talk about actual capacity. What is sent out here is this multiplied by your capacity, right? And the reason we are doing this is that we know that High Optic, right? This is High Optic, not Telecom One, actually has these factories. So we don't have to decide whether we're going to build them or not. We know we have them, right? So the capacity is 18 and 22 and 31. We're not looking at High Optic, so this is essentially 0, okay? Now, this would be the sum of all these values, right? And we know everything in yellow here and here has to be constrained to be 0. Also, this is sum of this. And what I want to do is to set up a generic model that would work. Then all you have to do is copy and paste and change the model here, okay? And so your total cost, or your, let's do variable cost and fixed cost separately. So your variable cost is some product. We're going to take all these costs, comma, all these, right? Your fixed cost is some product. In this case, you select all your fixed costs, comma, this, and your total cost is the sum of these two, right? So once you have set this up, you can now use the same thing for each one of those questions. So objective here We are, of course, trying to minimize this. All right. Our variables are only this. We're not selecting the factories because right now we know the factories exist. So your variables are just this. Your constraints now, the first set of constraints are these values because we are not dealing with telecom 1. We are only dealing with high optic. These values are going to be equal to 0. All right. And then the item sent out here has to be less than or equal to actual capacity. And now be careful here. The total amount sent out, we are only choosing one company. So that's equal to just these three. You're not going to select the next three because nothing is going to go into Denver, Omaha, and Portland because high optic is not working there. Okay. And so once you finish that, of course, all these values are integer. Assume non-negative is true, and you run your model. And so here you go. You have these factories. Baltimore sends 8,000 units to Boston and 2,000 to Chicago. Memphis here, Wichita is not being used at all, even though there's a factory, right? So you have extra capacity here. Memphis is operated to 100% capacity, whereas Baltimore is not. And here's the total cost. Now let's assume that you want to work on the other company, high optic. So let's create a copy of this. Now when you do high optic, none of this changes. This remains the same. You are going to put 0, 0, 0 here and 1 and 1 in this particular situation. You're going to delete all of these. And here, these two, you're going to delete these two equal to 0, but you're going to set this here in the constraints, right? Because you're no longer using high optic. You're only going to use telecom 1 factories. That's all going to be 0. Similarly, for demand here, you're going to change this demand. You're going to select telecom 1 demand, and that's equal to 6, 7, and 11. So that has to change. And so now you can rerun this model. And you can see here, well, here was high optic, here's telecom 1, and we have this model here. Both these models are working. There you go. Cheyenne is sending 6,000 to Denver, 7,000 to Omaha. Salt Lake City is sending stuff to Portland. Now let's copy it again, right? The next model assumes that we are merging together. So when things are merging together now, you have all 5 factories are available. None of this is equal to 0, so delete that. For demand now, this entire what is being sent to Atlanta, Boston, and Chicago can come from these 3 here. You don't have to make any changes here because you already have that less than actual capacity. And once we have this, we can now rerun the model. And you'll see now, since we have all 5 factories, you'll see some factories, every factory is being used. Baltimore is sending to Boston and Chicago. That's what they used to do. Memphis is actually sending to Atlanta and Chicago. You'll see Wichita, which was not being used, is now sending stuff to Omaha. And Cheyenne is sending it to Denver and Salt Lake to Portland. And this is the best cost. Now let's say that the argument is that, you know what? Maybe we can start shutting down some factories. So you want to figure out which one of these ones we should shut down. So now you've got to go to your variable, right? Remember, you hadn't selected the factories. Now you've got to select the factories and click OK. And under constraints, you've got to constrain these factories to binary variables. And if you rerun the model right now, it it'll say go ahead and shut down Wichita and shut down Salt Lake, and you'll save some money. How much money? Well, from 48 to about 47, that will come to about $1 million there, right? If this is in thousands of dollars, you're actually saving about $1.5 million. Okay, so you see now how you can actually model mergers and which factories to shut down using this approach. We'll stop here. This finishes network design. I'll be posting some practice problems and homework for you to work on. You should be able to either look at opening up factories or shutting down factories and be able to model both those kind of situations.